Okay, so we are doing 2.3 and 2.4, and 2.3 is rotations. And remember, we've got our rigid motion, which is a translation, a reflection, and a rotation. Okay, so a rotation is still rigid motion. Okay, the size isn't changing. And if we look here, we can see an example of a rotation. And this is rotating around point P, okay? Point P is the center. And if you look at this, you can see that the distance between the center of rotation P and B is the same as the distance between P and B prime. It's also the same between A and A prime, and C and C prime are also congruent. So if I don't need those though, I just wanted to show you that. So remember that rotations are measured in two ways. They're measured by direction, which would be clockwise or counterclockwise, and they're measured in degrees. Okay, the degree of the rotation. All right. Now, on the next page, you can see your vocabulary. A rotation is a transformation around point P, which is the center of rotation, okay? And the angle measure is called the angle of rotation. So let's look at a few of these on the page. And down, actually on 2 pages, page 90. And here is a rules for rotations around the origin, okay, of a coordinate plane. And when we do these, sometimes it's really hard to remember rules. I think it's easier just to remember what you're doing. And we'll talk about that tomorrow in class. Now I just want to draw a graph over here, and I'm going to place a point right here. And I'm going to call that point let's call it 4, 1. We'll write it right there. Okay, and if we look at a 90-degree rotation, and remember each quadrant is worth 90 degrees, the whole circle is worth 360. So if I go 90 degrees, okay, if I just rotate this, that point is going to end up right here. See how close the green point is to that axis? So if I go 90 degrees, it's going to be the same. And that makes it so we can see where they're getting negative yx from. We would have negative 1, 4. Okay, and 180-degree rotation would be 2 quadrants. And so I would go 1, 2, and that is going to land me right about here. And when I look at where that point would be, it would be negative 4, negative 1. So you can see the relationship on how that changes with those rules. 270-degree rotation would be 3 quadrants, and so it would be down here. And that would give me, what, 1, negative 4. And of course, 360 is completely all the way around the circle. We would end up right back where we were. And we'll do a couple of these in class. They're just a little bit easier for me to actually show you in class. So that's all that I'm going to do with rotations. So we're going to go on to 2.4, which is investigating symmetry on page 101. And we're going to look at 2 different kinds of symmetry. We're going to look at line symmetry, and we're going to look at rotational symmetry. Okay, so symmetry is where it maps a figure onto itself. Okay, and it has a line symmetry if you can draw a line that's called line of symmetry, and it's the same as a line of reflection. And which means is like that line is where you're going to make a fold. So if you look at this moon right here, here's the line of symmetry. And if I took this corner and I folded it down, that image is just going to lay right on top of each other. And that's what we call line symmetry. Okay, so if you turn the page, top of the next page, we have some examples here. Now I want you to pause this video and see if you can figure out how many lines of symmetry each one of these figures has. So if we look at the rectangle and you put a point here in the middle, you can see, I'm sorry, not a point. We draw a line here in the middle. That's going to fold down onto itself, isn't it? I also would have one through here. I can fold it that way and it would fold onto itself. Now if you look at this, sometimes you might think that you could do one diagonal, but if I put a diagonal line through that, those corners are not going to quite match up. So this has two lines of symmetry. Now this triangle, you might think that you could draw one here, and you could if we knew that this side was congruent to this side and these angles were congruent. But we don't really know that. So as it's shown, I'm going to write 0. And I mean, you could maybe say maybe, depending, but we just aren't given enough information there to pick any more. This last one would have a line of symmetry right there, and so that would have 1. Now at the bottom of this page, we start talking about rotational symmetry. And a figure has rotational symmetry if the rotation maps the figure onto itself. And we also have an angle of rotation, okay? So if we look at this star here, and here I have a center point, and I think about if I rotated this right here, I would not be able to tell that I had moved that figure. It would look exactly the same. And so the way they find your angle of rotation, they have the 72 here, is it's a fractional part of 360. And this thing has 5 angles that can be rotated onto itself. So they do 360 divided by 5, and they get 72. They also have an angle of 144, which is 72 plus 72. If I add 72 again, it'd be 216. And if I add 72 again, it would be 288. And that's how you find the angles of rotation. So turn the page, and we're going to do one example here. We're going to look at these figures again and see what they have. Now this square has 4 angles of rotation. Okay, I can move that 4, and so 360 divided by 4 would give me 90 degrees, and 180 degrees, and 270. Okay, this triangle, there's no way I can move one of those points to the other and it look the same. Now this arrow is pretty interesting. Do you see that if I rotated this 180 degrees, if I took this point here and rotated 180 degrees, that shape would still look exactly the same. So it has 180 degree angle of rotation. And that is all that I am going to do tonight in the video, and we'll do a little bit more, get into it a little bit more tomorrow during class. See you then.